Welcome to the Chapter 9, Part 7 Screencast. Now, a new idea is when we have two gases, and here we have them in separate containers, they're kept apart from each other, and if we open up a little hole in between the two containers, what will happen is the gases will diffuse into or through each other. So if we open up the little hole in the wall between the two containers, we'd expect red gas molecules to make their way into the right side container and green gas molecules to make their way into the left side container. And this diffusion process would continue until there's an even mixing of gas molecules throughout. So the concentration of gas molecules on this side and on that side would be the same. As you might suspect, the higher the temperature of the gas and or the higher the speed of the gas molecules, the faster they're going to diffuse from one side to another. Now we sometimes, instead of dealing with diffusion, deal with something slightly different, in which case we have gas molecules in a container, and when we open up the little pinhole in between the container that has the gas molecules in it and the other side doesn't have gas in it at all. It's a vacuum. And the escape of one gas through a tiny hole into a vacuum is called effusion, not diffusion. And what happens is when we make that opening, the gas molecules effuse through, and they'll do that until the pressure throughout is the same. So we don't really have a different concentration, and we have equal pressure throughout. Again, the speed of effusion, rate of effusion, is going to depend upon the speed of the gas molecules, which in turn will depend upon the temperature they're at and the mass of the gas molecules. Now, we can use this to determine some things. For example, if we know, we do know that the root mean square speed of a given gas is given by this relationship, equals 3RT over m, the square root. And if we consider having two gases, then gas 1 would have its root mean square speed equal to 3RT over the mass of its molecules, and gas 2 would have its root mean square speed equal to 3RT over the mass of its molecules. And this is an equation, this is an equation, and we can divide an equation by an equation, and we still have an equation. And if we do this, the 3 and the r, of course, will cancel out because they're the same. And if we do this at the same temperature for both gases, which we often do, then temperature cancels out. And so what we have is a ratio, oops, that's kind of a funny way to do that. We have a ratio of the speed of gas 1 to the speed of gas 2 is equal to, and what's going to reduce out of here is we'll have the square root of 1 over m1 over 1 over m2. Everything else cancels out. And if we now simplify this a little bit, we get that the rate of effusion of gas 1 compared to the rate of effusion of gas 2 equals the square root of the mass of gas 2 over the mass of gas 1. And note, rate of effusion here is going to be determined by speed of gas 1. So the root mean square speed of gas 1, rate of effusion gas 2 will be determined by the root mean square speed of gas 2. So let's use this in a problem to determine an identity of a gas from effusion data, and we're going to get that via molar mass. So suppose we have oxygen gas effusing at a rate 1.62 times more than some noble gas. Well, what we know then is the noble gas is going to be heavier than the oxygen gas because it effuses at a slower speed. And we also know that the rate of effusion of one gas compared to another is equal to the square root of the ratio of their molar masses, but inverse. And in this case, let's call oxygen gas gas 1, and the noble gas we're trying to find gas 2. And so the rate of effusion of oxygen, gas 1, is 1.62 times the rate of effusion of the noble gas, gas 2. So we have 1.62 over 1. That's the ratio of their rates of effusion. Note, we don't know the speed of either gas, but we know that the oxygen is 1.62 times more than the noble gas. Oxygen, of course, has a molar mass of 32 grams per mole. M2 is to be determined. And since we know everything but the M2, we can use normal algebraic techniques to solve this. We want to get rid of the square root by squaring both sides. And then 1.62 squared is about 2.624. The square root sign is gone. And now we multiply both sides by 32. And that gives us 2.624 times 32 grams per mole is equal to M2. And therefore the molar mass of the unknown noble gas is 84 grams per mole. And if you look on a periodic table, we'll see that that is the noble gas krypton. Now there's one last thing to be aware of, and that is that real gases are not ideal. We've been treating gases as if they're ideal. We've been using the ideal gas law, PV equals nRT, to describe them. It does a reasonably good job of describing lots of gases under sort of normal low pressure conditions that we typically find them in, but it's not very good for a lot of other circumstances. So here would be a test of ideal gas behavior for a real gas, how we would see if the ideal gas law represents it well. So if we make the ratio PV over RT for 1 mole of a gas, well, note, PV over RT is equal to N. And if we're dealing with 1 mole of a gas, then we're dealing with N is equal to 1. So PV over RT is going to equal 1, i.e. it's constant. And so what we would predict is if we graphed PV over RT versus pressure for an ideal gas, we should just get a straight line. In other words, as we increase the pressure, then increasing the pressure would decrease the volume. Suppose we keep the temperature the same and R the same, then this ratio would stay the same, and the ratio would not change at all. Okay, well, that's what we predict if the ideal gas law were to be valid as we increase the pressure for gases. Here's what it actually looks like for some real gases. As we increase the pressure and make a graph of that versus PV over RT for 1 mole of some real gases, we note that it starts out around 1 for all of the gases. And if we are at low pressure, then we're pretty close to what the ideal gas law would predict. But we go pretty far away from that as we increase the pressure in general. So here are some reasons why real gases are not ideal. Well, we've been treating them as if they have no attractions between the molecules. Is that true? No. Gas molecules actually do attract each other, especially as they get close to each other. And do gas molecules have no volume? Well, no. We've been treating them as if they have as if they're point particles. But if we squish a gas down enough, eventually the molecules will stick together, they'll form a liquid, and that liquid takes up some space. So gas molecules have volume. It's just often it's small enough that we don't have to mess with it too much. But if the pressure's high enough, then we surely do. So how do we describe real gases? It turns out there's several ways to do this. The most common is what's called the van der Waals equation. And if you note, it's kind of like the ideal gas law, except the pressure and the volume have been sort of adjusted a bit. They've had some little factors added. The volume, we subtract the number of moles times a constant that's specific to a given gas, which takes into account the volume of the real gas molecules. And for the pressure term, we actually add a constant times a concentration squared ratio, n is number of moles, v is volume, and this sort of takes into account the intermolecular attractions. And basically, one way to look at this would be a real gas molecule as it's heading for the wall of a container to hit it. It actually doesn't hit with as much pressure or with as much force as we would expect an ideal gas molecule to, because nearby gas molecules attract it and essentially kind of slow it down or decrease its force of colliding. Here are some tables of the A and B constant values for different gases, and notice they're kind of all over the place. Different gases will have different strengths of attractions and different size of molecules, and as you can sort of see, this is a bit of a pain in the butt equation to use, but we can use it to calculate more accurate pressures and volumes and describe gas behavior more accurately than the ideal gas law, especially if we're at higher pressures where the ideal gas law doesn't work too well. This is important to be aware of, but we're not going to really do much in the way of calculations with this, if at all. So that should do it for Chapter 9, Gases.